Okay, so for part two, we're going to talk about all the properties that intermolecular forces affect. Surface tension, boiling point, viscosity, melting point, vapor pressure, all these different features or characteristics that are affected by intermolecular forces. So when we talked about intermolecular forces last time, what we talked about is, how strong or weak they were, the London dispersion, dipole-dipole, hydrogen bonding, ion dipole, and all of these attractions between molecules, whether they're in their solid, liquid, or gaseous states, have different effects on different things. We're going to focus primarily on liquids right now. So let's start with surface tension. So if you've ever gone through a car wash and, you get the big ones, the one that's like $20 or $30, and you'll notice the water beads up. So if that's the surface of your vehicle, that's a water droplet, a beautiful water droplet. And what happens is, specifically with water, the intermolecular forces are so high that it's kind of coming in on itself. These molecules are all pulling in. And it's because the intermolecular forces are so strong that their attraction gets greater and greater and greater the closest to each other that the molecules get. Unlike something that's nonpolar or very, very slightly polar, maybe say rubbing alcohol, ethanol, methanol, those kinds of things, where we don't get such a defined edge. Okay, so surface tension, it's the ability for the liquid to minimize surface area. So what that means is the stronger the intermolecular forces, the higher the surface tension. So the increased intermolecular force equals the increased surface tension, okay? The more you want to minimize the surface tension, that means you have to have weaker intermolecular forces. So when we look at something like a paper clip on top of water, or those water bugs that can walk on top of the water like of a pond, what's happening is that thing, whatever that thing is that's on top of water, is not strong enough to break the cohesive forces, or the forces that allow the water to kind of come together and have a stronger surface. Your best example of this is elastic skin, okay? The elastic skin, not like skin on your body, but that kind of topical surface of a cup of water, a pond, a lake, something like that. We see insects land on the top of water all the time. They don't sink. The noodles for pools, like pool noodles, they don't sink. They're not strong enough. Well, buoyancy is another issue, but we're not going to talk about buoyancy. We're not going to bring that into it. But they're not strong enough to break the surface tension. Surface tension allows things to lay on top. So when we talk about surface tension, the energy required to increase the surface area at a given amount is based on a couple of things. It's based on surface area, it's based on density of the object, it's based on a lot of different things. Just know that generically speaking, that the higher the intermolecular force, the stronger the surface tension, means the stronger the energy required to break that surface tension. That's the takeaway I want you to know. So things that affect surface tension, strong intermolecular forces, which we just talked about, also raising the temperature. Raising the temperature is really important, even if we're not to a boiling point. Because when you raise the temperature, what you're in effect doing is you're increasing the movement of the molecules, even if they're not boiling. The more you increase the movement of the molecules, the more, let me say this, the less stationary attraction there is. So the more movement I can get, the easier it is to break through. So here are just some examples. We're going to talk about viscosity next. Viscosity, by definition, is the resistance to flow. Doesn't want to flow. Again, like I said in the previous lecture, if you were to take a capful of rubbing alcohol versus a capful of water, you're going to see that the rubbing alcohol is going to move much further than the water will. And that also has to do with surface tension because they're kind of coming in on themselves. So viscosity, or the resistance to flow, means the bigger the intermolecular forces, the larger resistance to flow. Okay, so I know I put a down arrow, but that's because more is a bad word. The stronger the intermolecular forces, the less it wants to flow. So that means the larger viscosity, because viscosity is by definition resistance to flow. So what we can say is the increased IMFs increases viscosity, which actually decreases flow. Or decreases, we'll say, length of flow. Okay. A good example is maple syrup versus water. If you pour maple syrup on a slanted, countertop, counter material, something smooth, not like wood, but just something smooth, like maybe a piece of plastic, you're going to see, clearly you can picture it in your head, the maple syrup is going to go much more slowly than the water. And again, resistance to flow. So factors that are affecting viscosity: higher intermolecular forces, larger attractions between the molecules involved. The more spherical the molecular shape, the lower the viscosity. They roll more easily. The less surface-to-surface contact, lower attractions. So again, you can see that how from part one and now part two, shape and surface area really play a huge part. So the more I can stack something, the more I can get these geometric kind of interlocking patterns, just the higher these forces will be. I know you guys have seen or can maybe visualize liquid mercury. Huge droplets. In fact, my very, very, very first semester here at USCB, we had a mercury thermometer and a student accidentally dropped it and it shattered. And we had balls of mercury just everywhere. We cleaned it up effectively and per OSHA and it was fine, and biohazard is fine. But if I had spilled water, I'd get puddles, as opposed to liquid mercury, which would be, they were literally, they looked like teeny tiny ball bearings. And it's, the first time in person I've ever seen mercury just spilled on the floor, as opposed to looking up videos or that kind of thing. But what that tells you is that the intermolecular forces of the molecules in liquid mercury are super, super strong. The fact that they form little teeny tiny balls as opposed to puddles should speak volumes to you. Also, raising the temperature. Anytime you raise the temperature of anything, you're increasing the movement of the molecules. When you increase the movement of the molecules, you are decreasing the intermolecular forces. Capillary action. Oh, where's a good place you could think about? Oh, if you've ever gotten your finger pricked at a doctor's office, right? Whether to check your sugars or your iron or whatever, they prick your finger to get a little blood going. And then they take this teeny, teeny, tiny little capillary tube and they just suck it up, right? They're not really doing anything. There's no plunger on the end of it. There's no thing that sucks it up like a what do they call those things? What you give medicine in, syringes. It's not like there's anything to pull it out. It just sucks it up. And the reason this happens, this capillary action happens, is because 1, surface tension, 2, viscosity, 3, cohesive and adhesive forces. So the skinnier the tube, the higher the liquid will rise. So these forces, these cohesive and adhesive forces, are working like an attraction, like a positive and a negative. So the adhesive forces attract the outer liquid to go up, and the cohesive forces hold it together in the tube. This is why when we talk about, reading a burette or a thermometer, or if I filled a volumetric flask, any of those things, not flask, a graduated cylinder, right? We always say read the bottom of the meniscus. The meniscus is the thing that's formed. This is water. And by the way, this is liquid mercury. Okay, so the reason a meniscus is formed, specifically with water, is because the bottom is really where it lies. These edges that go up, they're being attracted to the sides, in this case, of the test tube. All right, so adhesive forces, they're the ones that pull it up the sides of the container. You can see this is concave, where mercury is convex. And what that means is mercury just has much stronger intermolecular forces. So vapor and evaporation and vapor pressure, I'm just going to kind of ignore, now we want to ignore them. We'll talk about them. So intermolecular forces, the rule is the stronger the intermolecular forces, the lower the vapor pressure. You might think that's a little odd that they're opposite. However, when we talk about vapor pressure, we're talking about molecules leaving the surface of the liquid and applying a pressure onto that surface of the liquid. Okay? That's what vapor pressure is. We have molecules that have escaped the surface of the liquid, and they are applying a downward pressure onto the surface of the liquid. Now, if I have very strong intermolecular forces, very few molecules will escape the surface of the liquid with very little energy. I need lots of energy for something with strong intermolecular forces, say for example, water, to escape that surface of the liquid. So the weaker the intermolecular forces, the easier it is to get molecules to escape the surface of the liquid and then to go ahead and apply pressure to that surface of the liquid. So the higher the intermolecular forces, the lower the vapor pressure. The lower the intermolecular forces, the higher the vapor pressure. Because if I have low intermolecular forces or weak intermolecular forces, it's very easy to break all those molecules apart, have them escape the surface of the liquid, and therefore apply pressure to the surface of that liquid. So this is just, again, you don't have to memorize this, you just got to kind of understand it conceptually. So when we talk about thermal energy, the higher the temperature, the faster the rate of evaporation. That should make sense to you. So if I just put a bowl of ice on my counter versus a pot of ice and I turn my stovetop on, obviously the stovetop one is going to melt the ice much more quickly, boil it more quickly, and cause steam much more quickly. Does that mean the ice in the bowl on my countertop won't melt and then eventually evaporate? No. It just means on the stovetop it'll happen much more quickly. Here's your summary for vaporization. Vaporization increases with increasing temperature. That should be common sense. The rate of vaporization increases with higher surface area. So, for example, what that means is if I have like a little round cup, that has like maybe that size opening versus a big old beaker that's got an opening, like this, and I use the same amount of liquid, that's an important piece. Let's say 100 milliliters of liquid in both. What that's going to mean is the 100 milliliters in the biggins is going to evaporate much more quickly because there's more surface area for molecules to escape than the smaller one. We know that to be true just when we cook and we choose different pot sizes for what we want to do. So like if I want to cook soup really quickly, I got to watch it if I'm going to use my big 3-quart handled pot versus my 1 quart, which makes it a lot deeper, right? It's just going to take longer to heat up. And then the rate of vaporization increases with weaker intermolecular forces. So takeaway here, vaporization is endothermic. You need to put heat or energy in. Condensation is exothermic because it's taking those vapors and recondensing them, reforming those attractions and or bonds. And remember, anytime we break bonds or intermolecular forces, endothermic, recreating bonds and or intermolecular forces, exothermic. So when we talk about, some of these, we really have to be concerned with big picture.